אלכס, עדיין הולכים, נכון? רואים את המחוברים? כן, כן, אבל אין בעצם...
לא רוצה כלום, זה...
זה על השתית, אני על השתית. וזה בסדר.
גם מי שאיתנו עושים מיוט. אנחנו מחכים עוד מספר דקות לאחרונים, ואנחנו... We're waiting for a few more minutes and we will start national 3D printing event. Good morning, everyone. We are here in mapfield's first multinational 3D printing event on advanced materials and advanced applications. I'll say a few words in Hebrew and then we will start our day. I'm Raz, I'm the CEO of mapfield, and a few words in Hebrew. בוקר טוב לכולם. אני מאוד שמח עם הכמות המאוד מאוד מרשימה של אנשים שבחרו להיות איתנו כאן היום. סמינר ראשון, מרצים משש חברות שונות, ובחרתם להיות איתנו פה הבוקר ביום המיוחד הזה. אנחנו בימים של אין קורונה כנראה שלא היינו מגיעים למצב הזה שבו יש לנו לייב, מרצים מכל המקומות האלה. המכנה המשותף שלנו זה יישומים וחומרים מיוחדים ומתקדמים בעולם התלת מימד. אנחנו רוצים לפתוח בפניכם את עולמות היישומים האלה. אנחנו נדבר על חומרי גלם, על הפלטפורמות שאנחנו מביאים, ונביא לפה דברים שהם מעניינים, אני חושב, שלא נשמעו בעבר. הספקים שלנו מבינים את החשיבות של חומרי גלם ואת המערכות אקוסיסטם שלהם, רובם ככולם עשו על פלטפורמות פתוחות, ככה שכל אחד יוכל להרחיב את השימוש בחומרי הגלם. המשמעות היא גמישות שמאפשרת לכם הלקוחות לבחור את ספק החומר גלם ולמקסם את הפלטפורמה. זה פותח כמובן אופציה למחירים, לזמינות, ליכולת שליטה על המשתנים. הדברים האלה תחת קורת גג אחת לא הייתה עד היום זמינה. אנחנו במפעיל 3D מציעים מגוון של טכנולוגיות ויישומים, והמעניינים שבהם אנחנו נראה פה היום. יש לנו פריסת שירות ארצית, וזה מה שאנחנו רוצים להביא לכם. אני מקווה שיהיה לנו יום מענה ומעניין, ושתפיקו את המרב. ואנחנו נעביר פה לאנדרס להציג את הנציגים הראשונים, אז שיהיה לכולם יום נעים. תודה רבה.
Good morning, everyone. Thank you for the...
Hi, hi. Just a minute. I will introduce you. I will say a few words. Okay. I will speak in Hebrew, so after this I will introduce you in English, if it's okay. שלום לכולם, אני אנדרס, אני אחראי על תלת מימד ומפעיל, ואני המנחה שלכם הערב, הבוקר, לא הערב. חברת Asiga מתמחה בפיתוח וייצור מדפסות תלת מימד מבוססות טכנולוגיה DLP החל משנות 2011. Asiga Max ו-Asiga 4K, אחד המדפסות התלת מימד היותר מדויקות הקיימות בשוק היום. לפיכך, מיועדות לאפליקציות בהן נדרשות דיוק ואיכות פני שטח גבוהים במיוחד. למדפסת פורמט פתוח לחומרים פוטופולימרים מיצרנים שונים בעולם. בנוסף לחומרים ביוקומפטיביליטי, מערכת אופטית מתקדמת וייחודי, אשר יחד עם מהירות הדפסה טובה ואמינות גבוהה, מקנים למשתמש כלי ייחודי בתחומי מחקר ופיתוח, הם יכולים עם יכולות בעלות ערך מוסף בייצור התקנים מזעריים ברמת המיקרון. It's my pleasure to introduce Graham Turner. Graham is a VP Global Operation of Asiga. So Graham, you can start right now.
Oh. Well, there we go. Okay, thanks for the introduction, finally. Thank you. And for welcoming me and Asiga onto this webinar. So thank you, Mafil, and the team there. It's great to be with you. My name's Graham Turner. I'm going to present to you live from Sydney, Australia. And I'm the Global Operations Manager for Asiga. I'm going to go through what it takes to make and achieve, how to achieve a repeatable and accurate 3D printed object for production stability and continuity. So Asiga is a 3D printer manufacturer based in Sydney. We develop all of our own technology, all of our materials, and do all of our software development, all from our head office in Sydney, Australia. We have got two offices. We've also got an office in Germany, which is our European Centre for Technical Support. And they're also our applications hub that work directly with all the leading polymer manufacturers for a wide variety of industries. And I'll go through some of those key ones from an industrial application being Henkel and BASF. We've got a reseller network all around the world, and it's great to have Mafil representing us in Israel. So we develop 3D printers primarily for additive manufacturing of end-use components. The industries that we are classified as one of the market leaders in are audiology, so where they 3D print hearing aids or audio appliances. Jewelry manufacturing, all of our systems are high definition and suitable for manufacturing jewelry. We offer a superior level of accuracy and precision for dental applications for restorative and orthodontic and prosthetic dentistry. And also more recently with our larger Pro 4K system, we've attracted interest from just general additive manufacturing industries. So all Asiga 3D printers use DLP technology. DLP technology, for those that aren't familiar, is we use projectors to project images onto a photopolymer to cure that layer. And here's just a short video just to show. So our build platform there is plunging into a clear vat of material, and you can see the blue fluorescing UV light. As soon as that image is projected onto the layer is cured or polymerized, so it transfers from a liquid into a solid. And it will do this obviously for every layer. The layer thickness that you can print out on any Asiga system is arbitrary. So you can choose to print from 1 micron layers through to 200, 300 micron layers. And that all depends on the application. This, for example, is a jewelry manufacturing example. So typically 10 or 25 microns is fairly typical. Now, the reason we opted for DLP technology back when we began in 2007 was for 3 key reasons, really. One is that DLP offers a very fast production process. So we're exposing everything in that layer in one exposure. That long term, our systems, again, go into direct manufacturing environments specifically, and our largest market is medical manufacturing, so for audiology and for dental applications. So long-term stability is critical, and making sure that we can achieve that repeatability from print to print is really, really important. So the XY stability on a DLP system is maintained long term. The pixels refer to a mirror on the DLP chip. Those don't move in X and Y. They basically open and close to let light through or to block light. So we get good long-term stability on a DLP. And we've got a wide range of LED options available. And by LED options, I'm referring to wavelength of LED. So we have the ability to go into the deeper UV spectrum to process some really innovative new chemistries that are coming out all the time at the moment from many different material manufacturers. We find that in the deeper UV spectrum, materials cure much faster. You get a much more accurate, more defined print and much less light overcure. So the secret to 3D printing accurately, it is really quite simple. You know, we're producing parts layer upon layer to form an object. So the key really is to form those layers accurately. If you can't form layers accurately, and that's both in X and Y and Z, then if you can't do that effectively, then you will never be able to produce an accurate component. I think every 3D printer on the market has the capability of producing an accurate component. There's many different technologies, and those technologies serve a purpose for different types or different applications, different industries. We specialize in the high definition, high accuracy, and precision industries. And for us to maintain that accuracy across all of our customers globally, our systems need to perform on a repeatable level. But the key is that those layers are formed accurately. If you can't ensure that those layers throughout an object are formed to the correct size and thickness, you will never achieve a repeatable, accurate output. So this is just a slide just to show what a consistently accurate layer formation looks like and what an inconsistent layer formation looks like. You may find that the parts may look, the surface finish may look fantastic, but when it comes down to the fit in, say, a restorative dental application, this is where this varying layer thickness and layer size can play havoc and create problems. So we achieve our accurate layer formation via a number of technologies, which we refer to as process monitoring technologies. The number one technology in this list is our smart positioning system technology, where we not only drive our build platform down to a position, we detect that it's made and reached that position. So we detect for material flow and printer deflection. So as we're bringing a build platform down into a liquid resin, a liquid photopolymer that has a viscosity, similar to, in some instances, to like a yogurt, there's a lot of force required to get that platform down to position, and as a consequence, there's a lot of deflection that occurs on the printer. So our smart positioning system detects that deflection and also detects material flow. And this animation will show you how we do that. So this is an animation on our Max system. Here, the smart positioning system technology encoders are highlighted. We've got a build platform, a resin, and our DLP projector. As the platform approaches, those sensors are reading force. They're reading values in all four corners of that print area. And they will not send a signal to that projector to project the image until all of those sensors are reading 0. So as we approach, the sensors are active, material stops flowing, everything settles, the image is projected. So we know that we know exactly where that build platform is before we cure that layer. and that's accurate build platform positioning. So alongside this, you know, build platform positioning is one thing. You know, that's an incredibly important factor in layering. The second feature that we have in all of our systems is an internal radiometer. So we're projecting light images onto a light sensitive material. So the intensity of that LED or that light source is critical or super important to know how long to cure that material for. So we have an internal radiometer that's actively reading the LED power, and we will automatically adjust cure times based on actual LED power. So over time, when that LED reduces in power, we will automatically increase curing time. Alongside that, we've got a range of LED options. We really focus in the professional, in the medical market in our deeper UV wavelengths. We've also got the opportunity to produce printers in at 405 nanometers. So we've got 365, 385, and 405 nanometers. In the deeper UV, you get much faster curing. So you don't need to cure for as long, so you minimize the light bleed into the material. Also at that wavelength, we have the ability to produce water clear parts, and they're used widely across the audiology sector and dental sector, where they have certain appliances that need to be water clear and stable. We use very small pixels down to 27 microns on our Max X27 system. And we also accommodate all the unique behaviors of material when they're being cured. So they all behave slightly differently, whether it be light will bleed through the material at a different rate to others, whether some shrink more than others. Some materials are not as strong whilst they're being printed. So we accommodate all of those material curing factors within our curing profiles. And ultimately, the printers need to be robust and solid and rigid. Without a rigid construction, the systems will struggle to rebound. So they'll struggle to get back into position after that layer is formed. So as they come down to approach, if the printer isn't rigid enough, it will never quite reach position. And that's why many systems on the market today have varying results, especially DLP or SLA systems that use an upside down approach like ours. We also have a unique mode on our Pro 4K, which is called 4K mode. This uses a pixel shifting technology, or the technical term is wobulation. And that's where we nudge the DLP chip slightly inside the projector to overlap pixels to achieve a much higher definition. So we reduce the native pixel size down significantly. So on the Pro 4K80, this is an example, shows an object printed in its native mode. And then in 4K mode, the native mode is 80 micron, this pixel size. In 4K mode, it's 56 micron pixel. And you can see from the surface finish that the parts are noticeably different. You don't have that digitization on the part surface. So all of our Pro 4K systems are dispatched with the 4K mode as standard. Now, as far as 3D printing goes, you know, I think we're very happy with our the engineering on our systems. Asiga, since the beginning, we've always had an engineering focus, and we still are very much an engineering company at our core. But we know that materials unlock applications in additive manufacturing. And we've seen that growth in some industries significantly in such a short period of time. Specifically, if we look at, say, the dental sector, that industry has grown tremendously over the past 3 years, from just through the release of new dental materials for many different dental applications. So the way that we keep our end users up to date with this is to build optimized curing profiles with all the leading material manufacturers. This is across dentistry, it's across audiology, it's across jewelry manufacturing, and now more of a focus for Asiga is in the general additive manufacturing. And you're lucky to have somebody today from BASF on to talk about their materials. And it's great to see these big polymer manufacturers, you know, really focusing in on this, on additive manufacturing, and developing some really quite impressive photopolymers. So part of Asiga's focus now is that we are building our open material library. So we have the widest material compatibility of any 3D printer on the market today. We have close to, well, I think we've just tipped over the 500 material curing profiles. So we've got the compatibility with over 500 different materials from many different manufacturers. And this is a snapshot of our material library, which is growing weekly at the moment. It's staggering to see the interest and development that's happening across many different industries, specifically around 3D printing polymers. So I'm going to start with a relationship that we have with Henkel, BASF. I've got some slides after this. But with Henkel, the Henkel Loctite brand have developed quite a number of different materials for many different applications. I'm just going to run through some of them with you now. These are compatible with Asiga 3D printers. So they've got a range of materials from their 3843, which is a high toughness material. They've got a high temperature material which is their 3860 for temperatures up to 220 Celsius. They've got very good elastomeric materials. And I'm going to keep going through these, but these materials, when we started to develop curing profiles, so we work directly with Henkel, we work directly with BASF. When we start working with these polymer manufacturers, it's really quite clear that they have a noticeable difference to what we are familiar with, or what we have been familiar with since we began in 2007. There's been a real shift in the mechanical properties available now, especially for our technology, so especially for DLP. So again, this is another continuing the Henkel range. There's another high impact material in 3172. There's a tough material for dies for injection molding inserts. Asiga also has a material called Fusion Grey, which we've got documented on our website, where we've used that for injection molding inserts. There's another elastomeric material here. And then they've got a general purpose material, a highly accurate material, and an ultra clear material. So, and their clear materials work incredibly well on Asiga systems. The material that's really turning heads at the moment for Henkel is their 3955 FST, their flame retardant material. Now this, you can see the material image there. That's on our Max UV system. Those parts, that's what these parts were printed on. It's a unique material in itself, that it's self-extinguishing or flame retardant. It also requires some special processing to begin printing. So the material at room temperature is solid. It needs to be warmed to a temperature and then placed in the printer. And then our onboard heating system on all the Asiga 3D printers keeps that temperature at the designated temperature to continue and complete that print.
Resistance of this incredible material enable industries like aerospace, automotive, and mass transportation for the first time to produce end-use parts with additive manufacturing.
So we expect to see more of this material, but this is just a brief summary of how this is processed on an Asiga 3D printer. So first of all, we need to heat. So this is at our application center in Germany. So as you can see in the build tray, the material requires, it's solid at room temperature and it requires heat, to liquefy the material. Once it's in its liquid state, this it's ready for 3D printing, and this is a full build platform of electrical connectors from a large electrical connector manufacturer in Europe, and this is on our Pro 4K 80 UV system. So from a production perspective, this is our largest format 3D printer, achieving an accuracy suitable for restorative dental applications. So this isn't a large format system with low resolution. This is this offers an accuracy and definition that fits with dental applications. So these are just some images showing these connectors and the final product there. Then on to BASF. I can see I've got about a minute left of my presentation. So BASF, again, they really they're breaking ground when we talk about material characteristics, mechanical properties. They really are leading the way. They have a range of high temperature, high stiffness materials in the UltraCure RG series, and we've got the curing profiles for those in our material library, and also the ST series. And these are just a couple of components printed in their ST45 black. These have been printed on our Pro 4K 80 UV again, but they're available. You can print these materials on any Asiga 3D printer. And then when we talk about definition and accuracy, the resolution of our systems can go really down to really tiny pixel sizes, and that's when microfluidics come into play. This is a device that was developed by MIT in the US. It was a customized 3D printed unit to test drugs on tumor tissue. So it's to accelerate validating drugs for particular cancer patients. So this is the unit that was printed, where you can see with a microfluidic channel through. Now, just a brief summary. I've nearly finished. To hand over to the next presenter, but we've got three main products in our lineup. We've got the Max, which is, we recommend that for dentistry, for audiology, and for general additive manufacturing. So it's got a build size which will come up in the next slide. We've got the Max X, which is our highest definition system. That's quite a small build area, but it's suited for jewelry manufacturing, microfluidics, and there's lots of leading laboratories all around and research centers all around the world using the Max X. And then we've got our large format floor standing Pro 4K system, which is for dentistry, audiology, jewelry manufacturing. There's a mode for jewelry manufacturing and also general additive manufacturing. The build sizes of the printers, obviously this isn't to scale depending on the size of your monitor, but you can see the sizes there. And there's we feel that we've got a printer in our lineup for most applications. Obviously our systems can't produce a car body dashboard, but they will produce, handheld size components in the Pro series. And we're really happy that our development over the years has been recognized by some of the leading manufacturers across these testimonials that are popping up here across audiology and dentistry. They're some of the leading laboratories. So they rely on Asiga and the performance of Asiga to deliver the accuracy and the repeatability that they need in their production process. And that concludes my presentation.
Rafa, thank you very much. It was very, very interesting. You have a few questions in the Q&A if you want to answer.
What?
Can you see the questions on the top of the screen?
So yeah, so I'll just work through these. So the idea of continuous 3D printing is it's an attractive proposition. What you find with continuous 3D printing is that you need a dead zone within the material to allow for that, and you typically the accuracy that you can achieve with that is reduced. So our primary focus whenever we look at our 3D printing or 3D printing technologies and our 3D printers that we deliver to our users globally is that they offer an accuracy that is suitable for those applications that we target. That was in some of my earlier slides. But alongside that, which is incredibly important in a production environment, is the repeatability. So that's where all of our process monitoring technologies come into play. And then the speed of the system is the third focus point on our list. And I don't think right now continuous 3D printing can actually offer the accuracy and the repeatability that our systems can. Although Asiga 3D printers are far from slow. They're fast. They're not far behind a continuous 3D printer. But when you look at the accuracy and the repeatability of our systems, they sit higher up the chain. 4K mode isn't the same as anti-aliasing. Anti-aliasing is a manipulation of the external perimeter of the projected image. We overlap the pixels or wobulation, or pixel shifting is an overlapping of the pixels, which helps reduce the pixel size and the definition achieved.
Okay. Thank you, Raham. Thank you very much. It was very, very, very interesting. And thank you, everybody, for the questions. I will switch to Hebrew right now. So, Raham, thank you very much for joining us. Okay.
No problem.
Bye-bye.
Thanks for having me. Thanks, everyone.
טוב, אני רואה ששאלתם הרבה שאלות, חלק מהם אנחנו נעלה אחר כך באופן ישיר, כי זה שאלות מאוד ספציפיות. אנחנו גם נפרסם יותר מאוחר את הסמינר הזה, כדי שתוכלו גם לעבור, ותוכלו גם לעבור על השאלות שנשאלו עם התשובות שלהם. אם יש למישהו שאלות והם רוצים, יש לכם למטה כפתור של Q&A, אז תרגישו חופשי לכתוב. עדיף שתעשו את זה באנגלית כדי שהפאנליסט יוכל לקרוא את זה באופן ישיר ואז להתייחס בהתאם. עכשיו אני רוצה להציג את HP. אני בטוח שאין מי שלא מכיר את HP, חברת מחשוב והדפסת הגדולת בעולם, ושותף עסקי של מפעיל מעל 25 שנה. HP נכנס לעולם התלת מימד בסערה וקשה מקום גבוה בין יצרניות המדפסות התלת מימד, התעשייתיות ולפרודקשן. HP פיתחה מדפסת לייצור סדרתי של חלקים פונקציונליים באיכות גבוה עם חזרתיות דומה לייצור בהסרקת פלסטיק. זה לא טריוויאלי, ממש לא טריוויאלי בייצור בתלת מימד. חומר חדש התווסף ליכולות בייצור ב-MJF, לאחרונה הוא פוליפרופילן, חומר מאוד נפוץ בתעשייה, אני בטוח שאתם מכירים אותו, שהוא מאוד מתאים למגוון רחב של האפליקציות. מה שיותר חשוב לציין זה שהחומר הזה בפוליפרופילן אפשר למחסר, להגיע ל-100% מחסור תוך כדי הדפסה, ושאר החומרים שמדפיסים ב-MJF אפשר להגיע ל-80% מחסור. ו-MJF אין ספק שנותנת את היחס האולטימטיבי בין עלות לביצוע. It's my pleasure to There's Peter here. Peter.
Yes, hello. Hello, good morning. Can you hear me?
My pleasure to introduce Peter. Peter is the 3D printing application engineer of HP. And you can start.
Okay, thank you very much, Andres. Can you hear me? And can you see my screen, please?
Thank you. Yes, Peter, you can start when you're ready.
Okay, good. So first of all, thank you for the invitation. Good morning, everyone. It's a pleasure to be here. Okay, just let me start. Okay. So as Andres introduced me, my name is Petr Bartek, and I'm application engineer working for the HP. I'm covering the CEE and MEMA regions. Before I joined HP, I worked 4 years approximately in R&D departments for the different companies, naming just two. It was the Airbus and the Valeo. And after that, I joined the company where I was responsible for assembly lines and assembly technologies, mainly speaking about the plastic welding kind of industry. Okay, so mostly automotive, partly healthcare, and this kind of stuff. Talking about the HP, probably there is not much to say. I'm guessing that all of you know, or at least you are familiar with our company. So just a reminder, HP was founded in 1934 in the United States in Palo Alto, California. Today we have around 55,000 employees. We are operating with 170 countries. Our major businesses are computers and 2D printers, large format and small format. And in 3D printing, we joined in 2016 with our 4200 printer. Just a reminder for you, if you're not familiar with our technology, I will be sharing just 2 slides to explain you how the multi-jet fusion works, just very shortly. Okay, so actually we can divide our process into 4 steps. So in step number 1, we play the thin layer of the powder on a build platform. When talking about the thin layer, I'm talking about 80 microns approximately. In a second step, we apply the agents, which are the liquids we are using for fusing. And in additional step, we deliver the energy with the infrared lamps. Okay, so where we apply the agents in these places, the material melts, and this is how we create the solid parts inside of the build platform. I'm talking about the powder bed fusing technology. So there is no need to print or build any supportive structures because the powder itself works as a supportive material. So no extra cost or no additional cost on a supportive structures. If we take a look just shortly on our portfolio, what we have available right now. So we have actually 3 types or 3 branches of our machines. On the very left side, you can see it's a Jet Fusion 300 and 500 series. It's a great machine for prototyping. It's all-in-one solution, and we have actually 2 types of the printers. We have 540, 580. The difference is that 540 prints in monochrome mode, while the 580 is able to print in a full color. If you take a look on the picture in the middle, so you can see the Jet Fusion 4200 system, which was actually the very first machine we introduced back in 2016. It is desired for low volume or medium volume production. As you can see, it's a totally different kind of machine. It's a modular kind of system. Okay. As a further development, the last year, we introduced the 5200, which is, let's say, the continued development or of 4200 systems. So we can see that the machine looks kind of similar, but with the 5200 system, we applied many different or many improvements and many changes compared with the 4200. So 5200 is 30% faster, more reliable, and 30% the parts could be even 30% cheaper when talking about the price and comparing with the 4200 machines. Okay. So scope of this presentation is to introduce you a little bit about our materials and about our latest materials, because we have the open material platform, which means that we are working with some external partners like BASF, Lubrizol, And these are kind of companies, so it's not only about us who are developing the materials, but we have a wider cooperation in a worldwide level. If we take a look on a 5200 machine and our material portfolio, our basic materials are polyamides. Okay, so we have PA12, we have PA12 glass bits, and we have PA11. We have also elastomeric material. It's a TPU, which was developed in cooperation with the BASF company. And our latest material, and I will talk about it later during the presentation, is polypropylene, which was also developed by BASF. Just for comparison, let me share the material portfolio for 4200 machines. Okay, so we have also polyamides. So the family of polyamides are the same for both platforms. So PA12, PA12 glass bits, and PA11. And for 4200 platform, we have two elastomeric materials. Okay, we have TPA made by Evonik, and we have a TPU made by Lubrizol. The material I will talk about today is going to be TPA made by Evonik. But let's start with the 5200 platform and our latest polypropylene. So, well, why we actually choose the polypropylene? The polypropylene, or if you take a look on a pyramid over there on the left side, you can see that our materials are mostly semi-crystalline materials. The reason behind of it, it's exactly defined melting temperature, which is crucial to know for proper function of our system. So when we're talking about the MJF, we are mostly talking about the semi-crystalline materials. And why we chose the PP? So you can see that PP is on the very bottom of the pyramid. So that means that it's widely used. And when I'm talking about widely used, I'm talking about approximately about 38% of the whole plastic materials were used worldwide in 2019. Okay, so of all of the production of the plastic material, 38% was the polypropylene. So it's approximately 43,000 millions of tons. And just for your information, the other in the row are ABS, HDPE, and PS. These are the other mostly common plastics in the industry. But the polypropylene is actually the biggest one. So that's it makes perfect sense for us to be focused on polypropylene, just to enable some kind of applications which were not suitable for our PA family plastics. What are the benefits of polypropylene? So actually, you can see on the screen over here that on the very first one, I would probably name just excellent chemical resistance and low moisture absorption. That's probably, these are superior properties for some of the applications, and I will talk about it later, because this is the area we are willing to focus. As any other materials or any other parts printed on our system, I would mention that all of the parts from our system are isotropic. We have great mechanical properties, and talking about the polypropylene, we're talking about the ductile parts with great durability. Polypropylene has also outstanding welding capabilities, and I will show you later on what we are talking about, because we were testing all of the different methods of welding, and this is important for some kind of assemblies, especially short runs and some spare parts if needed. Okay. Additional or another thing I would mention is the cost-effective and high reusability. Okay, when talking about the cost-effective and high reusability, these two properties are kind of connected. So firstly speaking, the cost of the polypropylene is it is the cheapest material in our portfolio, and it is the cheapest material in general when talking about the injection molding and the plastics available. So that's why we took the effort and be focused on a polypropylene. And when talking about the high reusability, our polypropylene is low reactivity polypropylene. Okay, so that means that in theoretic manner, we can use 100% recycled powder for building parts. Actually, it's not, of course, possible because you have to add to the system some new material to produce the waste material. Okay, so when talking about the reusability, just theoretically, we can work with 100% reuse material of the waste powder. And this is also effective the final cost of the price. Okay, so you have cheapest material or you have the cheap material as an income. You can use 100% waste material, and this is affecting the final cost per part in a major way. Here are some mechanical performance or some mechanical characteristic for our polypropylene. So the polypropylene is now available only on 50-100 printer series. The values I'm sharing right now are for the balanced print mode. That means one pass. Okay. So you can see some of the values over here on the table. And let's continue over there. So I was also talking about the outstanding weldability capabilities. So we tested a lot of different methods from ultrasonics to vibration. So these are very common technologies in industrial use, and I have a lot of experience with them. Talking about sonics, it's really probably the mostly used technology for joining the plastic parts, and you can see that we tested all of the different methods together with the Axtel. Okay, so let me share just a short video. So there is no sound playing. I don't know why, but actually it's just the music behind, so you didn't miss any kind of information over there. What I just showed was the example of the laser waveling. So you can see that we welded transparent material to the base of the polypropylene, which is kind of interesting over here. When we talk about the possible applications, so it comes to the superior properties of the polypropylene. So I was talking about the great chemical resistance because the PP can withstand the exposure to many different chemicals where the PAs do not work, like the acids and some kind of solvents. I also mentioned the hydrolysis resistance. Okay, so basically no water intake by the material, so no change of the mechanical properties is happening. Okay, so based on these characteristics, one of the major applications we will focus on, or we are focusing on, are some fluid management systems. Okay, so it could be different gas or liquid separators, as you can see over there on a picture. So actually, this particular part was developed together with Oxler, and it's coming from the automotive sector, but it needs to be only automotive. On the next page, you can see door defrost vent. So this was kind of a big part, which was built in directly to the dashboard of the car. So you can see. Or as you can see, the parts are kind of big, and because of the low price and good properties, the polypropylene is great material for prototyping and for short run production. So that was actually the case over here for this part. So you can see the prototype of the defrost vent made by our polypropylene. When talking about the fluid management system, it could be also a lot of different pipes and tubes, let's say, in all different industrial systems, needing to be just automotive, but also air conditioning, whatever you can imagine. Another example. This is just a very, let's say, very simple one. These are the different fasteners. So we made to demonstrate the great properties of our polypropylene. So you can see that over here we have some flexible parts. Actually, it's some kind of a fasteners for cable routing system in a car and wire harnesses. So the parts itself, they're flexible but stiff enough to survive the opening and closing back and forth again and again. So another material I would like to mention today is the TPA. So the TPA was developed for the 4200 system. So at the moment it is not available for the 5200 system. For the 5200 we have the TPU made by BASF. So for the 4200 we have this new TPA. So what it actually brings, so TPA is flexible material. Okay, so it's also lightweight when you compare it with the TPU we have also for 4200 system available. It's elastomer part, it's elastomeric material with high part uniformity. I will show you what is exactly mean on the next slide. I would just pinpoint the high level of detail and color uniformity, which is it's a big step forward when comparing with the TPUs. And it's easy to process material. Okay, so when working with the TPA, the printing time is faster than on a TPU. You can use our standard 20-80% refresh ratio, and the natural cooling is available for the TPA. So that means that there is no extra or some additional step in the process, and you can let the material cool down inside of the cooling units or inside of the build units. So level of detail and colorful uniformity, you can see the evidence over here on the pictures below. Actually, this is when we are talking about elastomeric materials, we are mostly talking about different kind of lattices. Okay, so as we are willing to use this elastomeric material in some certain manners, we are developing or we are working on this kind of complex structures, which we call lattices. And with some other materials, it could be problematic to clean them properly. But actually, this is not the case with our TPA because it's very similar. The process is very similar to the PA's family. We have very good experience with. So you can see that even the cleaning of these complex structures is kind of easy. So actually, you can use the same process and same parameters as for polyamides, and you will achieve such a nice clean part. So if we take a look on a picture on the left side, you can see the level of detail I was talking about. So you can see a different diameters of the holes over there. So higher the line is, the higher the level of details we achieve. Okay, so for elastomeric material, because the behavior it's different when comparing with the PAs or with polypropylene. The dimensional accuracy is not on the same level, but as you can see over here, we did a quite good job in terms of accuracy and the level of details, because most of the small holes over there are visible and are open. So this is something I would like to pinpoint when talking about the TPA. If we take a look on a chemical resistance and the different temperatures, so you can so the TPA is resistant to water, some kinds of acids and hydroxides. Okay, you can see the conversion on the right side. These are the parts before the test, and on the left side you can see the parts or the testing samples after the test. Okay, we also check the weight gain of when we drown the parts inside of the oil. So there was some difference before and after. So it could actually absorb some percentage of the oil. You can see also over here some color changes when working with the peroxide, and you can see some severe deformations over here when working with the ethanol. Okay, so it's not like superior material, like not possible to withstand everything. But I still think that the possible applications are kind of wide. And we just have to choose wisely the working conditions and the condition the final part will work with. Let's take a look on some applications of the TPA. So as it is flexible material, so you can see over there on the bottom that that actually, you know, it's coming together. So some let's take a look on the industrial application first. So we have some fluid systems, so the flexible tubes and hosings. Okay, something like this. We have some robotics and end-of-arm tooling. So these elastomeric materials are great for prototyping and for final parts. And because of its tightness, it can work with the different pressures and different environments. So as an end-of-arm tooling, it's kind of you know, big industrial applications. So over here you can see some grippers to avoid damaging or scratching of the parts on the assembly line or on the production lines. The customers are using these kind of grippers to avoid scratching or deformations of the parts. We have some other applications over here. So these are mostly sports equipment. So let me mention the footwear over here on the left. So you can see pretty dense lattice printed over here, and it's actually midsole. So you have the outsole, you have the midsole, and then there is a shoe. The shoe itself is glue on the top. And this is actually the application we see a great future in. Okay, so in footwear, it's not for us. It's not only about just printing the part, but we would like to bring an end-to-end solution for our customers worldwide. So that's the reason why we are starting some cooperation with the big brands on the market. Okay, and starting to develop the process of production of the midsoles. Actually, what is the true benefit of it is that today you're mostly working with some EVA midsoles or similar kind of applications or similar kind of materials. So actually, it's mostly the foam. So the cushioning is equal, and the only thing you can do is actually adjust the thickness of this foam, and this is affecting the final properties of the midsole. Over here, with our approach, we design the complex lattices, and just with modifying these lattices in the different areas, you can define its stiffness. Okay, so this is the way to go, or at least from our standpoint. So our vision or the future of the footwear might be a totally customized midsoles for all different customers, because everyone is different. Everyone walks a different way, and has a different habit. So this is the way we want to go in terms of this application, in terms of footwear, and we are making big steps forward over here to allow or to bring this application to the market, to the real customers. Another from the sports equipment, another application I would probably mention are the helmets. Okay, you can see also some honeycomb structure over here. When talking about the helmets, I'm not talking about the outer shell, which has to be durable and tough, and impact resistance. But I'm talking actually about the inner parts of the helmet, and actually it needs to be only sports helmet, but also some military or working protective gear. Okay, so we work with the TPA because of its shock absorption properties. And just one application over here in the middle. It's a goggles for skiing or for the snowboarding. So it's gonna be, or it is flexible material. So, and it works perfectly in temperatures behind or below the zero. So this is another thing I would like to mention, that our TPA has a wide temperature rate of usage. Okay, also working in a below temperature where the others material could be, let's say, fragile. Okay, so the last but not least, it's automotive applications or some other industrial stuff. So you can see we are back in a fluid system, so different type of hoses and pipes, because it's a flexible, you can stretch them, you can bend them, and it's just working fine. For the functional prototyping, this is some crazy lattice structure over here. When I was, or for the functional prototyping of the lattices, we are playing, and this is something also interesting. We are playing with the custom seatings for some supercars, like super sports car. So the goal, or our vision is that the customer who is interested in such an expensive car will come to the showroom. The car manufacturer or the reseller will just scan his body, and according his unique anatomic, we will just print some of the components of the seats, which will be adjusted especially for this particular guy. Okay, and this will be implemented in the final seats of the car, also of course covered with some textiles or some leathers. But the benefit is that it's a cushioning for this particular person. Okay, so it's this is another application we would like to focus. When talking about the automotive, let me just mention that some because it's a flexible and we have the high level of detail, as I was presented, we are now able to enter, let's say, the interior components of the cars. So could be some part of dashboards, maybe some door panels and this kind of stuff. Because it is flexible, we can place it in those area with no harm to the passengers in when a crash happens. Also, some accessory parts for the car manufacturers. Let me just mention some covers. Okay. All right. So that was all I prepared today. So hopefully you like it. If you have any questions, go ahead.
Thank you, Peter. Thank you very much. Was really interesting. We have a few questions in the Q&A. You can answer. You can choose one and just pick one.
Okay. Let me check. So the question number one: what about PE? Any PE in the near future? Well, that's a good question. Unfortunately, this is something I cannot confirm. The way we go, it's a little bit different way, but we are playing with the TPE right now. Okay, so I think that's going to be another elastomeric material in our roadmap in a near future. Another one: what is the combination between the PP and the resolution? If I got it correctly, I think you mean the accuracy of the printing. Yeah, well, the behavior of the PP, it's a little bit different when comparing with the PA because of its high crystallinity. Okay, so the accuracy is not on the same level as the polyamides family, but we are pretty close, I would say. We did a very good job over here, and we improved these characteristics a lot. So we are very close to our polyamides originally. Okay. Good.
Thank you, Peter. For the rest of the questions, we will send an answer by chat after this. We are short on time, so we will pass for the next attendee, for the next panelist. So, המציג הבא שלנו זה miniFactory. אוקיי, לאחרונה למפעיל יש את הזכות לשווק את חברת miniFactory, זו חברה פינית שיצר מדפסת תלת מימד לחומרים אולטרפולימריים, כמו Ultimaker, PPOCU, PVDF וחומרים נוספים, גם מכונה לפלטפורמה פתוחה, שמשתווה אחד על אחד עם המתחרה בשוק היום, שזה פורקוס 450, במחיר אין מה להשוות, אז לכל מי שיש לו שאלה, אני אשמח שאחר כך תפנו עלינו ואנחנו נרחיב. So I want to introduce CEO, miniFactory CEO, Oli Pilachamaki. Okay, he will speak about special polymers for most demanding application. So Oli, thank you for joining us, and you can start when you're ready.
Okay, perfect. Thanks, Andres. Good morning, everyone, and thanks to mapfil for invitation to this event. My name is Olli Pihlajamäki, and I'm the COO at miniFactory. So my topic today is related on high-performance polymer 3D printing and how these polymers can be used in different demanding applications. Couple of words of miniFactory. So miniFactory was founded in 2012, and our company is located in Finland. First 5 years, we were manufacturing basic desktop PLA 3D printers like everyone did back then. But then last 3.5 years, we have had full focus on high performance polymer 3D printing. In 2020, our reseller network covers 15 countries in total. So what are these high performance polymers and applications where these materials can be used? So if we take a look of polymer pyramid, we can see different commodity polymers and engineering polymers, which are widely used with different 3D printing technologies. And most of these polymers we have seen a lot in material extrusion system. But these ultra polymers or high performance polymers can be found from the top of this pyramid. And due to the very high processing temperatures, these materials are mostly available for FFF or material extrusion technology. So up next, I will explain a little bit about these polymers and what these are. So basically all these polymers as a starting point, they can withstand high operating temperatures and wide temperature deviations. Mechanical properties can be up to 3 times higher compared to, for example, PA11 or PA12. Chemical resistance is extremely good, so these can withstand most harsh chemicals and solvents. Almost all of these polymers has flame resistancy, and these shortly or to summarize these materials can be used in applications where engineering polymers doesn't work or metal is not optimal solution. So why metal is not optimal solution? One reason is weight, since by replacing metals by polymers, we can save a lot of weight. And then at some environments when we are operating with harsh chemicals or solvents, at some cases, these kind of polymers are only option. Our printer is an open source system, which means the customer can use a chosen supplier to have these polymers. The reason for this is that when we have open material system, the customer can save up to 30 to 50% of material cost compared to those locked systems. And we are operating or cooperating with world-leading material manufacturers, so we can ensure the highest quality materials to work or to operate in our system. Next, I will show you a couple of examples, couple of use cases from different industries. So in aerospace, one of the most known 3D printable material is Ultimaker 9085. This material is certified for aircraft components, and when we take a look of commercial airplanes, most of the interior parts, panels, and these kind of plastic parts are based on this polymer. The material is FSC compliant with an OSO rating of 55 to 55, and naturally it's flame resistant material. This material is also can also be used in railway vehicles based on the EN 45545 standard. So the material is certified for train cabins as well. And of course, when we are talking about plastic parts, we are not manufacturing any critical parts. So, in airplane or aerospace industry, different covers, panels, brackets, and things like that can be easily be printed. In space industry, we have really interesting material. So ESD PEC, we also have pure PEC material as well, but I wanted to bring this ESD PEC to my presentation since this is the material what, for example, European Space Agency have been used in different testing and prototyping so far. So PAKK material is developed for space industry. Material has really low outgassing properties, so it can withstand those or that space environment really well. The material also has excellent resistance to wide range of chemicals and radiation as well. And of course, when we are talking about ESD material, different kind of ESD safe applications are first on table. And here in the picture, we can see a ESD safe electronic case. Electric vehicles, which is fastly growing industry in all levels. So we can see more and more electric vehicles. And when we are talking about electric vehicles, we can see the demand for a lot of parts to cover, to insulate these electric components. And for this purpose, we have quite interesting material called XTEM. The material is thermoplastic polyimide, and the material can withstand up to 240-degree temperature, and it has really high electrical insulation properties. So it's a perfect choice for different electrical application, and especially in these kind of electric vehicles. Motorsports. Finland is a promised land of motorsports, rally and Formula. So we have really nice example here in Finland. So former WRC driver Jari-Matti Latvala is nowadays building rally cars. He has his own garage, and he's printing a lot of parts to his historic rally cars. And the need for these kind of special parts is there, since these cars can be up to 20 to 30 years old. So there is no spare parts available anymore. So now they can print, for example, these kind of turbo intake pipe and different underhood parts to their rally cars. And for this application, there is material carbon reinforced PA6 to 66. This material can be up to 100% stronger compared to basic PA11 or PA12, and heat resistance is enough for these kind of applications. In medical sector, we have PPSU, and PPSU is standardized material for medical applications. PPSU is not for implants or anything in human applications, but for medical devices, it's a perfect choice. And a lot of different medical devices and things in hospitals are manufactured out of these polymers. Reason for that is that PPSU is sterilization capable. It can withstand repeated sterilization, including radiation, plasma, autoclaving, and so on. So it's a perfect material for these kind of sterilization tray for medical devices or other reusable components in medical sector. The material has extremely good chemical resistance as well, so it can withstand almost all harsh chemicals and solvents. And temperature resistance is also extremely good. One interesting application for material called Ultimaker 1010 is different kind of composite tooling. So nowadays, a lot of these molds are manufactured of metal, but now, based on the really good mechanical properties and high heat resistant, Ultimaker 1010 is widely used in different composite tooling. And for example, in the picture, we can see a layup tool or layup mold for composite manufacturing. So this material can replace metal in layup molds, and the material can be packed for vacuum and baked in the temperatures, or cured in temperatures what are required to make composite parts. So really interesting application for this polymer, and which makes composite molding really cost effective with this technology. Then of course, service bureau, based on the fact that when it comes to thermoplastics, miniFactory Ultra has widest material range available on the market. And reason for that is the chamber temperature. So the whole chamber can be heated up to 250 degrees, which allows us to print the most demanding polymers and polymers with highest glass transition temperatures. So with this heated and controlled temperature, we can control the parts perfectly during the process to avoid all the internal stresses and to ensure optimal mechanical properties for printed parts. I don't want to go too deep into these specifications, but a couple of things to pick up. So robust and repeatability is a key in 3D printing. So our printer has AC servo motors and ball screws in all axes, which ensure really high repeatability for printed parts. Then other thing is that we have a heated filament chamber in the system, so it ensures the optimal environment for materials during the printing. If without these kind of controlled material station, heated material station, the printing quality would start to suffer in a critical way after a couple of hours, even though the material would be perfectly pre-dried in advance. But these materials are absorbing moisture quite easily, just like PA materials. So with this device or integrated feature, we can ensure the high printing quality even in really long prints. Then top or cherry on our cake is miniFactory Arni process monitoring system. So this is a quality assurance tool which we have developed together with some of our OEM customers who are looking for ways to do the process monitoring and print certifications when we are printing parts, when we are printing different end-use parts. So how this works? Our printer is collecting data from multiple different sensors during the printing process. And when we are operating with thermoplastics, the temperature and the constant temperature is of course the key to achieve good results. After the print job, our computer software transforms all that data to paragraphs and visual 3D rendered picture of 3D printed part. So we can easily take a deeper look of printed parts. We can have line by line, layer by layer visualization of printed part. And in this software, you can go through each line, each layer, and see exact parameters that occurred during that layer or that line. And what makes this really easy to use is the visualization what the software offers. If there are some deviations in temperatures and the temperatures have crossed the set limits, the software is visualizing these deviation sections of the part by different color. So by combining color or from the color, we can see that, okay, for example, extruder temperature has gone below the set range. And in the picture or in the software, we can see the exact lines. So in the end, when some parts are validated by the customer, this is like eyes and ears for the user. So this can certify that the print has gone how it was planned to be printed, and there is not any hidden errors or hidden defects inside the printed part. User can fill some information in the software. So for example, spool number. So the end user can have full traceability for printed part. And this is extremely critical, for example, in aerospace. So the end use parts must be able to trace back to the raw material lot to factory level. So when we can fill the material spool number in here, we can add an operator name, date, and so on. So in the end, we can we can print out the documentation together with the part. So we can prove how the part was made. We can have full transparency for printing process. So this will increase the trust on 3D printing. And this is something that is very critical when we are targeting to print high quality end use parts. Then couple of our short list, what we can show in here about our customers who are using these kind of 3D printers. So we can see that there are some OEMs in railway, in space, material manufacturers, service bureau, motorsports, and then there is also some OEMs and other research centers in aerospace as a customer, but unfortunately we are not able to share everything. Okay, that was everything what I had this time.
Well,
thank you everyone.
Thank you very much. You have 2 questions in the Q&A. If you can refer.
Yes.
One is for continuous fiber composites for printer.
Yes, it's possible to print onyx material, but no for continuous fiber. miniFactory is material extrusion system, so FFF technology, and of course the accuracy. Basically, when the material is coming through the 0.4 millimeter nozzle, the printing accuracy or tolerance is plus minus 0.2 millimeter. But based on the fact that we have those AC servo motors and high repeatability, in some cases, if we know that we need to print, for example, 50 parts or something like that, we can print first 0 series part, take the measurements, and then adjust the process so we can achieve up to 0.05 millimeter tolerance for printed parts. Of course, this fully depends on geometry. So same basic guidelines are valid with our system that is valid with all the others material extrusion systems.
Actually, thank you for joining us.
Thank you.
Bye.
Bye. Have a nice day, everyone.
Thank you.
טוב, המציג הבא שלנו זה אנדריאה מחברת Ultimaker. חברת Ultimaker זה חברת הולנדית שיצאה דרך מטאורית ב6 שנים האחרונות, והיא נמצאת בשימוש על פס ייצור וחברות יצרניות גדולות בעולם, גם בישראל, חברות כמו וולקסווגן, פורד, BMW, לוריאל, היינקן ועוד הרשימה עוד ארוכה. זו מדפסת שזוכה בפרסים שנה אחרי שנה, מוגדרת כמדפסת השולחנית הטובה ביותר בעולם. וזה מעיד על זה שהם כל הזמן נמצאים בפיתוח מתמיד. הם עושים פיתוח לא רק של המדפסת, אלא של כל האקוסיסטם שלהם. Ultimaker נותן פלטפורמה גם של תוכנה, גם של חומרים וגם של חומרה. הפלטפורמה הפתוחה של חומרים מאפשר להשתמש כמעט בכל חומר שמגיע בצורה של פילמנט עד טמפרטורה של האקסטרודר מן הסתם. וזה אחד מהדברים הכי טובים במדפסת הזאת, החופש שנותן לנו בשביל להשתמש, החופש לאפליקציות, יותר נכון. אז אני אשמח להציג את אנדריאה. I will introduce Andrea Gasperini. Andrea is a business development manager, EMEA at Ultimaker, and he will speak about unlocking engineering and specialty materials potential on Ultimaker with industry validated application. So Andrea, you are with us.
Yeah, can you all see well my screen?
Yes.
Fantastic. Okay. Well, Andrea, Sofia, thanks a lot for the invitation today. Actually, yeah, it's really a pleasure to also share with you our work globally, also with our resellers as well and sales partner. So my name is Andrea Gasperini. I'm part of the business development team here at Ultimaker. Today I will talk to you about the really application-focused presentation with our top stories from industry customer. And also, yeah, what I want to share with you is most importantly, how does it benefit the end user and the machine actually that we are promoting here.
Andrea.
Yeah.
You need to change your display. Okay.
Oh.
The full screen.
Yeah, you are not in full screen.
I'm not in full screen. Which screen am I sharing? Sorry.
Okay.
No, now we are seeing your PowerPoint. F5.
Like that.
Now we are.
You see your desktop.
You are see your desktop.
See my desk. Okay. Jesus. Okay. Now you're seeing this, right?
Yes. Only. Yes. Full screen.
Okay. And now what you see?
No, something don't look good.
We see you in the editor mode and not in the participant mode. You need to change your display exactly.
Yeah.
Or swap with that.
Like that.
Yeah.
Exactly. Now it's okay. Thanks.
All right. Perfect.
Okay.
Okay, I'm gonna stop this as well. Okay, sorry guys. Yeah, so what I want to talk to you now today is about, so everybody knows a little bit about Ultimaker, and of course, when you think about Ultimaker, you think about only, the first thing that comes to your mind, it's the hardware in this regard, and you know, we have a pretty reliable printer. It's a low total cost of investment here. We have different models that are desktop type of printers with a temperature range that goes up to 280 degrees. But on the other side, also we have other pillars of our ecosystem, which are the software, the Ultimaker Cura. At the moment, we have around 6 million users active, has a lot of extensive plugins that can be used to really extend the capabilities from also third-party provider. And then we have, I'm gonna just shift this, otherwise I don't see it. And then also another pillar for us is the services. So is the academy, where we actually give trainings on all the different facets of additive manufacturing, specifically the FFF technology and how you can design parts and use the software Cura embedded in the system. And today, I think the core of my presentation will be actually how we leverage the potential of the material ecosystem that we have developed at Ultimaker with our open filament system and all the type of application that can be actually produced. So our open material system, it's as you might know, we are not limited by any restriction in terms of material use, as long as it's 2.85 millimeter filament. All the ones that are available on the market can be used on Ultimaker. We have at the moment more than 180 material that have optimized print profile for all the models of our printers that we have currently on the market. And we have established a pretty strong material alliance program where we really work together with the material suppliers to leverage at maximum the potential of the material and the processing technology. Of course, it's very beneficial to have a open system as long as it's easy to navigate, it's really easy to understand, and it's also possible to discriminate between several features of each of this category of material that we have in our system. And our system is mainly composed of three categories of material. The first one is the Ultimaker materials. They're really generic type of material, can go from commodity to engineering, PLA, ABS, PVA, TPU. All these materials features are RFID tag, so they are right away recognized by the printers. And then there we have on the marketplace and on Cura, we have optimized print profile per each material and each color. And then we have a pretty detailed documentation of each type of material with the technical specifications. The second part of the second pillar of our material ecosystem is the material alliance material. We have around 120 material at the moment that are mostly functional. So they have a unique property of functionality compared to the generic Ultimaker material. So here, these materials are actually characterized by also optimized print profile per each material, per each model of the printer that we have. And each material there has a really clear as well documentation that can be accessed on the marketplace and on Cura. But the open system actually has its own reason to exist if it's also possible to use infinite material that are available on the market. And here we're talking about higher temperature material that have an extrusion temperature above 280 degrees, up to 350, for example. There are customer grades, so that you produce yourself in your research facilities and they're not commercially available, or also third-party generic from other material suppliers. Again, can be BASF PLA or another Levos polyamide. And all this material also, they have an incredible number of different features that are also easy and necessary to be considered. So today, as I promised, I will share with you really an application-focused presentation where I will bring to you some example of the application that we have developed with customer using the material alliance material, and as well some material that are actually fitting with the open system materials, for example, high temperature material and custom-made filaments. So let's start first with the first type of material that I will talk to you about today. It's composite. So it's a blend of a thermoplastic matrix with a stiff and short fiber reinforcement. And then here we have, for example, I want to show you today the first use case that we have developed in collaboration with the Dutch Army and the material manufacturing DSM of Novamid 1030 CF. Where actually in the Army use extensively additive manufacturing to create parts also to deploy on the field. And in this case, I really would like to believe me here that they use this hook that was printed here in our facilities, that I have it here, to really lift a tank of a couple of tons, 30 centimeters up in the ground. How was that possible? So it's really useful to really work closely with the material partners here to really exploit and leverage the full potential of the material that they have created, and also on our side really to exploit the maximum potential that the machine has to really boost the mechanical performance. So what we did together with DSM was really to start deep diving into different type of designs for this type of hook. So we created 4 different models, where then analyzed with the finite element analysis using Digimat software and the FEA software to really identify the area where the maximum stress was occurring and also the potential failure mode per each model. And then we were really stressing the part in a controlled environment before testing and understanding which is the maximum load that that specific model can really withstand. And then, as you can see, we were really iterating as long as the maximum, the best, or at least the load specific for that tank was achieved. The second use case is an automotive case. This is coming from a racing team here in Netherlands. It's called Van Amersfoort Racing. Is a really clear example of one of the capability of Ultimaker printer to have a multi-material product where you can have a part where you have two different material extruded together in the same part. So in this case, the application is a side pod blower. Initially, this was the initial solution was really a collage of different pieces, metal pieces, bolted together and really homemade, and it was really not easy to replicate, or it was not fitting for a different design of the car. So they wanted to go for the additive manufacturing solution, and here we really work on a really close relationship to really achieve such a complex end product that is actually composed of two different materials. So the stiff structure, so the internal structure that you can see in the middle is produced with the Clarion PLA GF10 composite material, really to impart stiffness, rigidity, and also to basically have it also lightweight structure compared to metal sheet. And then the outer part instead has to fit within the car, so not to have to scratch it. We have a really good cushion effect and actually seal very well in order not to have any air blowing outside of the part. Was really produced with our TPU, Ultimaker 95 Short A TPU. Then I want to step into a second range of material that are always part of our material alliance program, which is the post-processable material. And here I'm really presenting one solution, which is the stainless steel material that is coming from BASF. Is called 316L, so it's a grade of stainless steel that is normally used in industry. And here what we are targeting is really all the small and complex parts that are really featuring really large assemblies that are unnecessarily expensive to be produced by other means like CNC or metal injection molding or many other technologies. And also what we want here to target is all the thousands of specialized production and assembly tools that are actually used in your mechanical workshop on your concrete floor. And as well, try to target all those applications that usually are produced in plastic, but then they have a bit of a certain limitation when it comes to harsh environment usage. So here the benefit of this technology in a nutshell is really increasing decrease the cost of production for metal parts, producing lightweight structure that you can in metal. So because using an extrusion technology, you can actually have an infill part inside and reduce the weight of the metal part instead versus a full density part. And as well to have a faster iteration design for your parts in metal. But as you might know, not all the part that you produce with the 316L are not ready to be used. Actually, you need 2 extra steps along the line that are the debinding and sintering step in order to have the final part. But the good thing about the solution that Ultimaker and BASF is bringing is that we are not forcing anybody to actually in-source also the equipment and the knowledge to perform the binding and sintering. You only have to in-source the 3D printers and the material to create a green part. Indeed, all the outsourced steps, the debinding and sintering, are actually performed by a service provider that you might find also in your region. That's something we need to verify. It's also available in Israel, but I'll be happy to give you some more information as well about that. And then, as you can see, you only have to perform the printing step, which, for example, for a pump impeller would last 5 hours for a total cost of 40 euros, and you outsource the debinding and sintering steps, and it would take roughly 2 to 3 weeks to be performed with a total cost of 24 euros. Therefore, you're going to get your final part, a pump impeller that I have here in my hands, for the cost of 64 euros total versus the 1,000 euros that you normally would pay for such a part as a spare part. Here now is some example of the application that we have developed with customers. The first one is a fixture for welding machines. So as you can see here on the top part, that was the original part made of plastic, was really not feasible for a long-term run, so that therefore there was an interest to substitute that with a metal part. And this is how in last year the BASF team actually was able to provide this solution to UTMAker 3D additive, and really made it in perfectly in 360 now. The other example is the pump impeller that I show now. So BASF had also a lot of pumps around in their plants, and what I show here is they had to substitute a pump impeller in their centrifugal pump, and that actually was a good case to really made it in stainless steel and apply that in the pump. And the last example is the metal grips coming from one of our sales partner in England, through GBR here, where they use the ultrafuse 360L really to produce metal grips that then were actually used as a good use case for example, gripping certain packages in a packaging line. Then the second part here is I want to talk to you about a new material that came out last year. It's basically the complementary support material for PVA. So we know that PVA actually is a really good support material for thermoplastic material, but it has certain limitation. Therefore, actually Aquasys 120 is really basically covering that limitation by actually being able to use this material support for inert polymers. So I'm talking about the polyolefin of this world. I'm talking about polycarbonate, PVDF, and all the high temperature polymer, because this is a material actually has a pretty good high temperature resistant. Indeed, it has a pretty high storage modulus at high temperature, about around 120 in a heated chamber, but also up to 220 as well when it comes to extrusion. So to have a contact with an extruded part is really based on a new motif, which is called the reinforcing microfiber technology that Infinite Material Solution owns. And as well, it's a really easy to dissolve material, actually dissolve in warm water around 50 to 70 degrees without any need for a specific solvent or soap to be added. One key part of it is that differently from PVA, it has a really low moisture absorption, about 0.2 weight% maximum compared to the 10 weight% that normally PVA would have. Then I'm going to switch to the section of open material system, and here I'm showing you something really outside of the specification of Ultimaker for now. So it means it's a material that can be definitely used on an Ultimaker, but is outside of the specifics. And this is the PPS carbon fiber. It prints extremely well. It's part of the family of high temperature thermoplastic. We're talking about a material that has a peak temperature resistance of 240 degrees for a really short time, and a pretty good and constant stability around 210, 220 degrees on stable working operation. So here an example of a part that we have been producing with a tier 1 automotive company for one of their facilities, and is a turbo motor component. And then on the right side, actually just a benchmark print really to show you the quality of the prints and the surface quality of the part. My last example for today is here to talk about custom-made filaments that actually can be used on our printers. And here the example of Lattice Services, which is a French company working in the biomedical sector, and their goal is to produce personalized breast prostheses. And here is their product. You see a pretty thin, really complicated, and really biocompatible material. And how they do that? Actually, they make their own material. So they make their own filaments that they use extensively for their facilities. So here we're talking about polylactic acid, glycol acid, and also polycaprolactone. And then they're really biocompatible and also bioabsorbable by the body. And they have developed their own print profile actually to be used on their print farm of S5 printers that is really necessary as a low volume serial production tool for their personalized medicine mission. So with this, we'd like to wrap up at least the benefits that the open material ecosystem is providing to the customers. So the first thing is the openness. Really, you can stay up to date with all the new development material, and you have the freedom to use the top material that are available on the market with no restrictions. And this really allows you to print really fancy parts, really complicated design, and really high-end material. The second part is really more material we have on our marketplace with the optimized print profile. So really to have an easy to use experience, then the more application you can unlock. And the other part is working closely with material partners for OEMs like we are on the hardware side is really a must to boost the performance of material and really bridge the gap with existing manufacturing technology, like can be CNC or can be even injection molding. And the example of the hook and of the side pod actually is a really good example. With this, I would like 1 second to invite you all for the webinar that we organized with BASF on the metal printing with Ultrafuse 360NL. It's going to be live on December 9th. And of course, I would like to thank you all for the attention. And again, Mafil, for this invitation. Happy to take any question. Thanks.
Thank you very much, Andrea. It was a very nice presentation. You have a question.
Okay, so here you see, can you supply biocompatibility approvals? So Ultimaker does not. We are happy to help you passing as a sort of support consultative to really pass the test when it comes to the relationship that the hardware feature has on the final part extruded. For example, if we have to change a different type of grease on the bearings, or we have to change the tubing because it's really affecting the chemical properties and the chemical part of your filament or of the extruded part. That's something we can do. We don't do those type of certification or approvals because we don't have the capacity and also the capability of doing so, but we're really happy to support there in this, like we did for Lattice services.
Okay. Andrea, thank you very much. Thank you for joining us.
Thanks a lot.
Yeah, bye. אוקיי, אז טוב, אנחנו מתקדמים, עברנו כבר 4 מציגים, היה מעניין מאוד, אני יודע שזה ארוך, נשאר לנו עוד 2, אני ממליץ בחום להישאר, זה יהיה מאוד מעניין, מקווה שיש לכם קפה ומים קרוב עליכם כדי שתוכלו גם ליהנות מהמצגת. המציגים הבאים שלנו זה חברת BASF. אוקיי? BASF היא אחד החברות הכימיקליים הגדולים ביותר בעולם, הם מייצרים חומרים לכל התעשיות, והם נכנסו לעולם התלת מימד לפני כמה שנים, וכפי שאתם יכולים לראות גם במצגות שעשו המציגים הקודמים שלנו, כולם מתייחסים ל-BASF, הם אחד השחקנים הכי חזקים בשוק, אנחנו במפעיל בחרנו לייצר אותם בארץ, בגלל הפורטפוליו הרחב שיש להם, הם מוסיפים מגוון מאוד רחב של חומרים מרוכבים בשילוב של קרבון, שילוב של סיבי זכוכית, וגם חומרים מטאליים, כמו שראיתם עכשיו שאנדריה הסביר, ואני בטוח שעכשיו הפאנליסט הבא שלנו גם ירחיב על זה. אז I want to introduce Dr. Engineer Matthias Fischer. Matthias is a BASF application technology. So thank you for joining us, Matthias.
Yeah, thank you very much for your kind introduction. I will try to share my screen. So also very warm welcome from my end. Short question, can you see my screen in a full mode?
Yes, it's okay.
Perfect. Yeah, thank you very much to be here today. Today I would like to give you an overview of our product portfolio, especially with our solutions in the filaments. And yeah, my name is Matthias Fischer. I'm from BASF. I'm application technology manager for 3D filament printing. And yeah, before I start with my presentation, I would like to give you a short overview of our activities, of the 3D printing solutions from BASF. This company is a subsidiary of BASF, located in Heidelberg, and it was established already in September 2017. We are now present here under the brand Forward AM, and we have superior material and solutions for additive manufacturing. And our team is about, it was beginning of the year about 150 people. I think at the moment it is already more than 200 after the acquisition of Sculpteo in France. And we have several application technology centers. Of course, one big part is in Heidelberg, but we are also active in Emmen in the Netherlands, where we have also our filament production. That's also the location where I'm usually located when I'm not sitting in the home office. In general, Forward AM has, let's say, experience, or is based on BASF, or is using the experience of BASF in the product development. We have really good access to the R&D in BASF in Ludwigshafen. We have, due to these, let's say, decades of experience, we have also access to several applications here in the industry, from normal or standard polymer engineering. And in general, we can be, of course, only as a customer like that, to be a one-stop shop for all AM technologies. And we have really large portfolio. Portfolio means from different AM technologies. I have here on the next slide a short overview. So we are very active in the powders for the powder bed fusion technologies. We have also liquid formulation systems, so photopolymers and inks. A third technology is the filament technology, where I would like to talk about today. This includes several plastic filaments, but also the metal filaments. We got already in the previous presentation here from Andrea a nice introduction for the metal filament, which I would also like to pick up again in my presentation. And if let's say are more requirements than just about materials, we also offer solutions concerning additive manufacturing services, which can mean about design optimization, support in scale-up activities, for example, or also sometimes tests to identify the right material and the right printer technology for a potential application, because sometimes it's really not so easy to say from the beginning on if maybe laser sintering system is the right solution for a certain application, or if it's rather a filament. What we saw in the past is that all these different technologies can have advantages and disadvantages, and it's really hard to make a, let's say, a right solution from the beginning on, especially when maybe also the experience is limited concerning additive manufacturing. At the moment, we have several ultra-fused filaments in our portfolio, which can mean we have standard products like simple PLAs or also PET filaments, also sustainable products, where we have at the moment a recycled PET filament available. We have several engineering filaments where we think that they are really very important to push this whole industry in the professional sector for several applications. And I mean, in the general world of plastics, there are so many different products available. We are not limited to BASF core materials, so we are also using other materials where we think that they are important to push the additive manufacturing industry in total, which can mean, for example, advanced PLA grades like our PLA Pro 1, but also other materials like PPs or ASA materials, optimized ABS grades for 3D printing with reduced warpage, for example, but also grades which are reinforced with fibers. I will explain later a few more details about that. I also saw, sorry, there's a small mistake here in the slide. It's a PPG of 30, not a 60. Unfortunately, not yet. Yeah, maybe somewhere in the future. And we have also high temperature materials like a PEI 9085 and a PPSU, which require, of course, a little bit, or which have more demands concerning the printer hardware. We have also several flexible grades in the portfolio, like TPC, TPE materials with different shore hardnesses, also a TPU, which is based on the BASF TPU portfolio, where we have an 85A grade available, but in the future we will also follow several other grades here in the next, let's say, weeks or months. With support, we are working with HIPS or BVOH. BVOH is a very nice water-soluble support material, which dissolves very easily in water and has also a very, very nice printability. And at the moment, concerning metals, we have the 316L filament in the portfolio, which is also printable on, let's say, most desktop printers. Concerning the industrial use of materials, we have, let's say, we are of course developing our products on BASF knowledge, but we also think that a reliable product quality is very, very important to push these, to push the whole AM market in general. And as customers usually expect from industrial material grades, from injection molding, but maybe also from extrusion, is that you have a really good product documentation, which means customers are usually expecting safety data sheets, but also technical data sheets. And here we are really working hard to provide also these products for our filaments, which means we are providing data sheets for filaments which are based on printed specimens to give our customers really a feeling how a material performs, not only in the best suitable build orientation, which is usually the flat one, where you can expect the best, let's say, behavior in general, but also in other directions, like the upright build orientation, the Z direction, where you see usually, the main disadvantages here in the filament printing. We are also participating in material partner programs. For example, we are present with several grades in the Ultimaker marketplace, really to enable our customers to find a very, let's say, to have a very quick success with our materials on a 3D printing system. If we talk about our standard filaments, sustainability is a question which is popping up more and more often. And customers are asking us about sustainability. At the moment, we have one product here. It's a recycled PET filament, which is usually, let's say, PET is usually a standard product, easy to print in general. But with regard to the sustainability aspect here, it's a very interesting product. And I would like to share you today one application where this product was used for. It's about a surfboard from the company Juju. And here they use this PET filament for the core of the surfboard. Of course, to get the right mechanical performance, the right stiffness. There was a coating done afterwards as a strong structure. But it's a very nice example how such a sustainable product can be part of such a customized, environmentally friendly surfboard. Furthermore, we have, let's say, more engineering grades in our portfolio. And here I would especially highlight the reinforced plastics, where we have at the moment several grades available. In general, if we are talking about reinforced products in filament printing, we have, of course, several benefits, like an increased strength in the flat build orientation. We have also very high stiffness usually, which means the Young's modulus is usually very high due to the fibers in the product. Also, the temperature stability is increased. So we are usually talking about the so-called heat deflection temperature, short HDT, which is increasing whenever you enter fibers in your product. And we have also lower shrinkage due to the fibers. A nice side effect is also that the aesthetics are usually also increasing because you have a nice black surface, slightly rough, which is nice to have. Yeah, let's say the layer is not so visible than usually in 3D printed parts. Of course, this fiber reinforcement also leads to several challenges, yeah, you will definitely get a higher anisotropy of the part. So usually these fibers are nice for the flat orientation, but you have definitely challenges in the upright orientation. Whenever you have the chance to heat the chamber of the printer, or let's say you can close it with a cover to increase the environmental temperature of the build environment, you can reduce this effect, but in general, yeah, it's still there. So that's of course one of the challenges which you need to take into account when you are working with fiber reinforced products. And also an increased wear in the hardware is visible. It means you should usually use hardened nozzles, make sure that the printer has also driving gears, for example, which are suitable for these kind of abrasion critical products. So, sorry, that was a little bit too fast. So concerning our products, we have at the moment 5 reinforced products in the portfolio. These are 3 glass fiber reinforced filaments. One of them is a PP, so polypropylene reinforced with 30% glass fibers. Maybe some of you already got the information this year that we took over the business from Owens Corning, which means we have also now filaments like the PA GF30 and the polycarbonate GF30 in our portfolio, which have also really nice performance with regard to the stiffness due to this high amount of glass fibers in the product. You can see here a fan on the left side, which was printed with the PP GF30, which can be used, for example, in automotive industry. Concerning carbon fiber reinforced products, we have a PET with 15% carbon fibers in the portfolio, which has a very nice aesthetics. I would say it's a really very nice product, easy to entry product in printing of carbon fiber reinforced products, because it has really nice printability, nice surface finish, and also the overall material performance with regard to stiffness and the strength is really very nice. Polyamide based is a PHT CF15, which has an increased temperature stability, but also extremely high stiffness. It's, I would say, the filament with the highest stiffness in our portfolio, with a Young's modulus of about 8,000, with about 8,000 megapascal in flat build orientation, which is really, yeah, very impressive for a filament product in general. When we come to high temperature materials, we have at the moment 2 products in our portfolio. It's a PI 9085. Maybe most of you know them as an Ultim material, Ultim 9085. But we have also PPSU grade in the portfolio, which is based on the BASF polysulfone product category. And I will explain you later on a few more details about these kind of filaments. In general, when we talk about high temperature products, we usually should first make the definition of the temperature resistance. We are usually doing it with 2 methods. It can be either the heat deflection temperature, which is a special measurement method to see how stiff a material, or how stiff a material is with an increase in temperature. But it can be also the so-called Rickard softening point according to ISO 306, which is based on a hardness test. But it's, in our case, it's not so common. We are usually using the HGT value, which is also nice for engineers, because with this value we can already, let's say, at least estimate how the stiffness of a part will drop at a certain temperature. Concerning the PPSU filament, I would like to give you a short use case here, an overview of a use case. So a while ago we had a use case here. It is about a pressure drop optimized air duct, which was target for this application was in aerospace industry. So was an aerospace case study. One of the tasks was here to reduce the pressure drop. Means the task was really to guide air from one area to another area here in this air duct with a minimum amount of loss of pressure. Which means the flow of the air needs to be optimized, and there was a further restriction, and this restriction was that there was another component in this area where this flow should be guided to, and it was let's say a challenge to get the right design to guide the air from point A to point B. At the end of the day, we got the design here on the left side. So that was the result of the first study to improve the airflow. If you have a look on this design, and I mean, whenever you worked already with 3D printing, especially with filaments, you immediately see that's a part which is not easy to print. Yeah, so the design is not really optimized for the FFF printing. Second challenge was that we've also strict restriction here for materials for aerospace. So of course, you need to fulfill certain mechanical properties, but also flame retardancy, for example. At the end of the day, our engineers split this design into pieces. You can see it here on the on the right side. Yeah, so we had two pieces. One piece is here the green one, the other one is the blue one. Splitting this design into two pieces enabled us to print it, let's say, upright in two different parts, and we joined them afterwards while using I would say very smart clip and glue connection in the connecting area, and we used the PPSU filament here to produce this part. The motivation to use a PPSU was in this case that this filament has a very good mechanical properties in the flat orientation about 65 megapascal, but even in upright, of course, printed on a printer with a heated chamber, which was around 180 degrees C. We have still about 50 megapascal in tensile strength. If you see here on the right side this picture, you can see this connection area. You can see that we use a reduced infill. That's also why you have this triangular structure in this component. So it was more or less printed with a reduced infill. But the combination of the reduced infill and the material made the part really extremely stiff. And it was at the end of the day 173 grams and printed with two contours. HTT is really quite high with 212 degrees C, and this is the HTT at 1.8 megapascal. So this is the higher load value. Yeah, whenever you have a look on this HTT values, you need to check: are you looking on an HTT measured on which load? Yeah, because there are two different loads available in the standard. One is at 0.45 megapascal, which is quite low. The other one on 1.8. And we have also passed several flammability tests according to FAR 25. All right, so far about the plastics. Now I would also like to give you a short overview about the metal filament. We got already some basis information here today, so I will just repeat it shortly here. In general, the metal filament is a product which can be printed in almost all FFF printers, desktop printers. We usually say whenever you can print an ABS, you can also usually print the metal filament. Very easy to print, also safe in handling, so you have no powder. It's really a filament, which is easy to handle. You can print hollow structures like you know it from the FFF printing process in general. And afterwards, you have a so-called green part, which means you have a polymer part with a very high-filled metal powder inside. And you can also post-process this part, like grinding, like polishing already before you give it to the following debinding and sintering process, which is necessary to get really the metal properties afterwards. It can have also cost advantages to other methods. I would say it is not always competing with SLM, but especially for small parts, It can be quite cheap. It depends also a little bit if you have already an SLM system or not. Of course, if you would have already a system in-house, yeah, it's maybe not it has not so nice advantages. But whenever you would think about to buy an SLM system for a couple of €100,000, it's of course a very interesting alternative solution which can be used in-house for printing. In general, you need to print the part first. So we talk about here green part, and then we have a debinding and sintering service, which is afterwards sintering the parts, or first of all debinding the parts. So which means reducing the polymer matrix of the part. It will shrink. And it's about 20% in the Z direction, and in the XY about 16%. So you need to consider this already when you print the parts. So you need to print them usually bigger, but therefore we have really good processing guidelines. And afterwards it will be sintered. Also, it's the same service provider because concerning or in between those kind of steps here, debinding and sintering, the parts are getting very brittle because the polymer matrix, the strong material in between, is gone. Yeah, after the sintering process, you have a final metal part. So here I'm also coming already to my last slide. So when you have the metal part, you have maybe not the question, hey, what can I expect here? Which kind of mechanical properties can I expect? And of course, we have also here a difference between the flat and the upright build orientation. Yeah. So of course, in the Z direction, we have also the issue that we have, let's say, that we are limited here to the anisotropic behavior of the filament printing process, but in general, you have still a tensile strength, which is, let's say, at least almost in the area of the XY direction, but especially the elongation of break is much lower. But we are talking here about tensile strength about 500 megapascal, which can definitely compete with the MIM process, but also with parts which are printed in the SLM process. Of course, it depends always on the porosity of the part, on your print settings, also on the post-treatment, like polishing, for example. But in general, you can expect parts which are, yeah, really quite compatible concerning the mechanical properties. So now I'm coming already to the end of my presentation. I would like to thank you very much. And when you have questions, please let me know. I will just check if I can see the chat.
Hey, Matthias. You have any Q&A?
Yeah, so I see it already. We concerning PP. Yeah, we are, let's say, PE is something which is at the moment not really in high focus. This question is coming up more and more often, but I would say at the moment there are not so high demands for PE development. Whenever you have, let's say, a really potential application behind with high demands, maybe it's something where we can talk about, but in general, it's yeah, at the moment not so high requested. So then we have activity regarding combined metal and polymer printing in terms of material compatibility. Yeah, that's of course not so easy. I would say in general, it makes definitely sense to combine metal and polymers, and we did it in the past. At least once I can remember that we printed grippers with the metal filament, and then we used TPU inlays to get, let's say, a protection between the gripper and then the actual part which was gripped with this gripper. But this has been done with two different, let's say, in two different steps. So we printed single metal and then single polymer. Metal was debinded and sintered afterwards, and then it was connected, because you have, during the sintering, you have usually temperatures of, I would say, more than 1000 degrees C. So every polymer will definitely die. And then we have the last one. Difference between traditional composite with GFCF to the materials to be printing applications. In general, yeah, you are very, I would say, the core behavior is really quite similar. Yeah, so you have really the anisotropic behavior, which you need to take into account. But I would say we are usually we're working with short fiber reinforced filaments that it's easier to print. And yeah, then you have let's say the challenge, or let's say the difference is that you have, let's say, more possibilities to change the direction of the fibers, and you always need to take into account that you have no connection in the Z orientation. But in principle, let's say you have similar challenges in this technology. So whenever you have, let's say, very good experience in composites, very, I would say, good knowledge in composites, I would also say it's maybe even easier for you to understand the behavior of an 3D printed carbon fiber reinforced part.
Okay, Matthias, thank you very much for your detailed and clear presentation. It was very nice. Thank you for joining us, and enjoy the rest of the day.
Thank you very much to be present here, and have a nice day. Bye.
אוקיי, אז הגענו למציג האחרון שלנו. היה מאוד מעניין עד פה, אני מקווה שאתם נהנים. ההצגה האחרונה היא חברת סינטריט. אוקיי, סינטריט, למי שלא מכיר, זה מדפסת SLS, מדפסת דסקטופ, מדפסת מצוינת שהיא בעצם נכנסת לנעליים של המכונות הגדולות של SLS, רק שהיא דסקטופ. ואז הרבה יותר נגישה לרכוש אותה, זאת אומרת, במחיר אין מה להשוות עם הטכנולוגיה של SLS שכולם מכירים, ויש לה יכולות מרשימות וגם יכולת הדפסה של מגוון רחב מאוד של חומרים. החברה מייצרת 7 חומרים, מבוססים על ניילון, מבוססים על TPU, אבל כמו שהמדפסות שאנחנו מוכרים היא גם פלטפורמה פתוחה, אז גם חומרים אחרים ניתן להדפיס, זה אחד מהיתרונות הבולטות שלה, גם החומרים, גם הפלטפורמה וגם המחיר, אז לכל מי שיש שאלות בהמשך, אז נשמח להרחיב. I want to introduce Konrad Glowacki. Sorry for that. Konrad is a co-founder and a product manager on Sinterit.
Hello, everyone, and it's nice to meet all of you. Today I would like to speak with you about potential materials for desktop SLS systems. But first of all, I'd like to introduce a little bit about me. So I am a co-founder of the Sinterit, and my background is software engineer, but in general, I am in this business for many, many years now. And currently, my main focus is materials, both materials that we currently have in portfolio, materials that are in the pipeline right now, and the whole future of materials that looks really, really promising as I look on that. And I would like to tell you a little bit more about Sinterit, because we are a company that started a real push on desktop laser sintering machines. And we started that with laser machine shown to the market in 2015. This was the first easy to use small machine that you can just buy and use for a laser sintering parts. And then 2 years ago, we introduced a new machine called Laser Pro that enables to use even more materials into the systems because built-in nitrogen chamber. So in the results, this really good opportunity to grow a base for the new materials. But in general, the whole thing about laser sintering is not to have just a printers, but to provide the whole complete solution for that, the whole ecosystem to running that, to make it easy and affordable that every business can use it. and this is our goal as a company. There will be some more thing to that, but I will mention that on the end of the presentation, because today I'd like to talk with you about materials in SLS in general. And essentially in SLS, you use powder to sinter that with laser to achieve the final part of this. But that means that the powder material that you use in that it needs to have some unique properties to properly flow and to properly melt and to enable really good printouts out of that. And it's not easy thing. It's not easy to make a powder that it's great, and that's why it's not so many powders yet on the market. But there is a way to change. I think most of you saw SLS parts, the white parts, and it's more than 90% sure that it was just PA12 parts, because this is a standard for SLS printouts till today. That the usual material for that is PA12. It's for 25 years now the standard for SLS. And of course, we as Sinterit introduced the first material. It was PA12 smooth, because we decided that, okay, we need to go a little bit further and get really great details out from the PA12 parts. So it's, I think, the smoothest PA12 material that you can get on the market. This was the unique thing with that. But we decided that we need to go further and to introduce even more materials for that. So then we also decided to introduce more better mechanical material, PA12. So this material is great mechanically with high elongation at 55%, but also with tremendous impact strength. So you can really easily make casing for tools that will survive real heavy-duty work. But then are the rubbers. Essentially, rubbers are not so easy to process with FDM printers, but with SLS and the freedom of lack of support structures, it enables to even more application that are possible with rubbers. So that's why we introduced TPU material called FlexaGray, just for prototyping of rubber parts. This was the basic to start with working with rubbers. But there's a lot of different rubbers that could be used. So then we decided that we should dig into that there's way more things that we can make with rubbers. And that's why we got a really soft touch TPU material with a shore hardness or 45 shore A scale, which is great material for really haptic devices, anything that your customer would like to touch or you would like to provide into your product. So this is the uniqueness of the material that we introduced. Then we also saw that there is a need for more better mechanically TPU, and also to see some more color. So we got FlexaBright as the next also TPU based material, which is potential to dye, so to make colorful parts out of that. But in general, with great mechanical properties and real good details, it can get some really good cosmetic models, but also even medical aid models that can be used by medical professionals. And then we saw that, okay, we have also other kind of materials that are good to have. And we also got the TPE, which is a material that could be used for medical devices for skin touch medical devices. But also we have a sealer that can be water and airtight and get a piping out of that. But also it's great for work even with gasoline. But we haven't stopped there. Just a week ago, we launched a 7th material into our offer. And this material is PA11 ESD. So with this material, we decided to bring even more functionality into the materials. So it's safe from electrostatic discharge material with way better thermal properties, even HTDB at 170 degrees. But it also PA11 that it's based on castor oil. So this adds a little bit more on eco-friendliness of AM here. And this material we introduce with electronics industry in mind. So we see this material in FDM printers, but also we see that in SLS we can get even better with that material and deliver a solution for final assembly lines and tooling and different other application there. And beside that, there is additional market for explosive atmospheres where this kind of material are really in need. So right now we have 7 materials in our offer, but we believe it's not all. We believe that there is also always a way to have a third-party material, other materials that we have now, we see right now. And that's why we believe in the openness of the system. So I think that we are the easiest to start and really open SLS solution when you can just use whatever else material you want. And this is our principle as a company, that we think it will grow the market. And what does it mean for you as for the business? It means that you don't need to only rely on our materials. There are other alternative suppliers for the materials. So we see this as a growing industry right now. We, of course, get the best material into our offer and offer that directly, but we cannot stop anyone from ordering PA12 from other supplier. And we believe that's the option that we should enable. And then there are other types of materials that for now are as niche, but if you want to source them from other suppliers, you can go freely and get it. And of course, we are constantly in touch with customers, and if something is really worth, we also help them, and also at some cases we bring that into our offer later on. But it's utilized not only by business but also by research institutes. We saw a lot of work around different additives tests that could be performed pretty easily with the system. And for making new powders, new polymers, and this kind of openness and small machines for desktop laser sintering we provide enables fast iteration with a need of really tiny amount of powder. You can start even with like 500 grams of powder to do a real test on the final system, which is really unique for SLS as a whole. And we see a lot of universities, hundreds of universities utilizing our machines for teaching of using SLS and exploring the new materials and new additives. And in the end, right now, we are seeing more and more new powders coming out from the universities that we will see that can show up on the market and get commercialized in next years. And this is essentially what we believe this work that with openness, we can really broad the spectrum of the powders. As for example, with Ultimaker, there's a broad portfolio of materials you can select. And we see that with really close relationship with research and customers and their applications, we can really boost that up. So essentially, to summarize that, we know that PA12, it's mostly used right now, but we believe it's not all materials are necessary in SLS, and this needs to grow. And right now we deliver the most of material in desktop laser sintering solutions, and they are ready to use right now. And as we believe in openness, we see that in the future, there will be way more materials, and in the following 3-4 years from now, there will be dozens of materials to select. And right now we have like 5 materials in the pipeline and many more in the future research plans. Before I finish, I would like to also let you know that beside the current situation in the world, we are working continuously to extend our offer. And tomorrow we'll be launching a new product from Sinterit. You can register for a webinar for that product and to see more in detail what it will be. I can't share yet the details, but for sure it will be really useful for all of you, especially if you have not worked with powder yet, or you work with big industrial SLS machines. I would recommend to go and see how it really works with desktop SLS solutions. And I would like to thank you for your participation, and thank you, Mafil, for inviting me for this webinar.
Thank you, Conrad. It was very interesting. Thank you very much for your presentation. Thank you for joining us. טוב, תודה רבה. היה פה המון חומר, היה מאוד מעניין. אני מקווה שנהנתם, מקווה שלמדתם דברים חדשים. היה עמוס ממידע חדשה, אז אני בטוח שיש לכם הרבה שאלות. בשביל זה אנחנו כאן. אנחנו זמינים בטלפון, מייל, כל דרך שתרצו בשביל ליצור קשר איתנו, אנחנו זמינים ונשמח לענות על כל השאלות. אנחנו גם, יש לנו חדר הדגמה עם כל הציוד שדיברנו עליו היום, שתוכלו לבוא ולהתרשם. מי שעוד לא מכיר מוזמן להגיע, גם לעשות בנצ'מארק אם יש צורך. אנחנו בית אחד שמלווה אתכם בכל התהליך, אוקיי? בשביל למצוא את הטכנולוגיה המתאימה, למצוא את החומרים המתאימים, בסופו של דבר שאתם תצליחו בהדפסות שלכם ותצליחו בפיתוח של המוצרים שאתם עושים. אז תודה רבה שהצטרפתם, ואני מחכה שתיצרו איתנו קשר. דבר נוסף, לפני שאנחנו מסיימים, אנחנו בסוף שנה, וכמו כל סוף שנה, מדינת ישראל אוהב לעשות מבצעי סוף שנה, אז גם אנחנו, קשרו עלינו, יש מבצעים מאוד אטרקטיביים עכשיו בתקופה הזאת של השנה. אני בטוח שתמצאו את המדפסת שמתאימה לכם, וכמובן עם המחיר שמתאים לכם. אז אנחנו לרשותכם לכל דבר. תודה רבה שהייתם איתנו, נתראה בפעם הבאה. להתראות.